Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next. Before we do that, let us quickly recall whatever we discussed in our previous lecture. You might recall, as I shown on the screen, we discussed in the last lecture about the nonlinear applications of operational amplifiers, specifically the performance of comparators. As you all know, a comparator is a device which compares two voltages, and the output will change to either VCC or minus VCC depending upon which voltage applied to either the inverting or the non-inverting inputs of an operational amplifier is larger. We have got different varieties of comparators. We discussed a simple comparator, which can also be considered as a zero crossing detector. We also looked at an inverting comparator, an IC comparator like LM339, and we also saw a regenerative comparator, that is a comparator with a hysteresis. So, these are the various circuits that we have seen. Now, let us move on to find out whether we can also have other types of comparators. One of the very important type of comparator is called a window comparator. A window comparator is basically a comparator which has got a threshold voltage, threshold voltages which are corresponding to a lower limit and a upper limit in voltage. One can set this lower and upper limit in the any range that you require within the 0 to VCC or minus VCC to plus VCC. So, a window comparator therefore will have again two definite thresholds corresponding to lower tripping point and an upper tripping point, about which also we discussed in the last lecture. And so, you would be able to detect input voltages which are within these two limits. So, for voltages which are within these two limits, you will have a particular output state. For all other voltages which are either below the lower tripping point or above the upper tripping point, you will have a different state, output state. So, this is what the window comparator will do. It will show whether a given input voltage is between specific two limits. Now, I can just give you a very simple circuit which is a window comparator, as you can see on the screen. Because you have got two definite threshold levels to set up, you have to have two comparators. Each one of the comparator will be associated with a very specific threshold. For example, the A1 operational amplifier, which is at the top, has got an LTP as one of the threshold, while the A2, which is at the bottom, the second operational amplifier, which is here used as a comparator, has got an HTP as one of the threshold. The other free inputs of both the op amps are connected together, as you can see in the figure, and that is the point at which the input voltage can be given. So, when you give the input voltage here, these two comparators have got two different thresholds corresponding to LTP and HTP or UTP, and therefore, whenever this voltage goes beyond these limits, you would find something will happen at the output stage. Now, these two op amp outputs, we have connected diodes D1 and D2, and we have combined the two outputs together, and through an RL we are looking for the output voltage at this point. So, this is a very simple circuit where you have two operational amplifiers used here as a comparator, and you choose through two of the inputs for the two op amps as LTP and UTP. the other two inputs, free inputs, are connected and given to the input. The output of both the op amps are connected through diodes, and that is the output that we monitor. Now let us assume that the LTP is plus 3 volts by some means. Maybe I can use a potential divider and give a voltage which is 3 volts from the VCC. Similarly, I have the HTP here. I have taken an example typically as 4 volts, which can again be considered from the same VCC by using a potential divider. So I have a 3 volts as the LTP and 4 volts as the UTP, and now if I give voltages here which are going from 0 to a larger value, maybe 0 to 10 volts or 12 volts. As I keep on increasing the input voltage, what will happen at the output is what we should ask ourselves now. Now as I increase this voltage, as long as this input voltage is less than 3 volts, you can see it is less than the LTP in this op amp, and therefore 3 volts will be larger than the input voltage in this op amp A1. So the output will be plus VCC, trying to go to plus VCC, because the plus input is larger than the minus input. So you would find when this becomes plus, the diode will conduct and you will get a high voltage at the output. So as long as the input voltage is less than 3 volts, the output will be high, and that is what is shown in this graph. If you see, starting from 0, output is high, nearly Vsat, the saturation voltage, till you come to LTP, till you come to the 3 volts. In this case the LTP is 3 volts. Now when I go beyond 4 volts, let us assume the input is more than 4 volts. Input is more than 4 volts. Here this 4 volts is more than 3 volts, therefore it will be minus at the output in this A1, but minus here will make the diode open. It will not conduct, because diode has to be forward bias with a positive voltage on this side. Because it is a negative Vsat, the diode is off, D1 diode is off. Whereas if you look at voltages more than 4 volts, in this second op amp A2, you find this is 4 volts, more than 4 volts, means the plus input is more than the minus input, and therefore the output becomes plus Vsat. The plus Vsat again will make the diode conduct, and therefore you will get a very high positive voltage at the output. So for voltages which are less than 3 volts or less than LTP, you get a high as you see on the graph, and for voltages which are above 4 volts, again you get a high at the output. Now let us see what happens when I am at 3.5 or 3.1 or what, any voltage in between the LTP and the HTP, 3 volts and 4 volts in our case. So for any voltage in between, it will be more than 3 volts but less than 4 volts, that is a condition. It should be more than the LTP, more than 3 volts but less than 4 volts, the HTP. So when it is like, let us typically take an example of 3.5 volts. So when the input is 3.5 volts, let us look at each of the comparators. A1 comparator, 3.5 is more than 3 volts, and therefore the output should be minus. If the output is minus, the diode is blocked, so it is not conducting, is open, therefore nothing comes at the output point. Because this is 3.5 volts input, if you look at A2, 3.5 volts is still less than plus 4 volts which is connected to the other input, therefore still the 4 volts is larger than 3.5 volts, and therefore the output will be minus again, and therefore this diode is also open. So both the diodes are open, therefore no voltage comes from any of the comparators, but the output is connected through RL to a ground, and there is no output voltage, and therefore this output voltage will only be ground voltage because it is connected to ground through the RL. And therefore as long as the input voltage is more than the LTP, more than plus 3 volts, and less than 4 volts the HTP, the output remains 0, and that is what is shown in the graph by the side of the circuit. You can see the output is high till LTP is reached, and at LTP it comes to 0 and remains 0 till it reaches UTP, and beyond UTP if you increase the input voltage you get high at the output, V sat at the output. The x axis of course is V in and the y axis is V out. So, this is the basic principle of a window comparator. You see, I am able to now detect all voltages which are between two limits. Whenever I get a 0 output, I know I am within the window. Whenever I get a voltage more than 0, that is V sat plus V sat, I know I am out of that window. I can be either more than the higher tripping point or less than the lower tripping point, but I definitely know it is not between the two window limits. So, this is the principle of a simple window comparator made out of a very simple 741 op amp. You can do this with ordinary op amp 741 and you just use two ordinary silicon diodes and you are ready for the comparator. Now, we can also have a variation of this circuit, so that the output is not low within the window, but high within the window, and it is 0 for every other voltage. It sometimes be more useful if I have the output of the comparator 0 all the time, only when the voltage is within the window plus and minus the LTP and the UTP, then you get a high voltage at the output. For all other voltages outside the window, I get 0 volts, will be a better scheme. So, how do I make that? The simplest way to make that is that you can perhaps use a standard IC comparator. In this case it is called LM339. I mentioned that even in the previous lecture. The LM339 is quad comparator. Quad means 4. So, in LM339 you have 4 comparators in one package, and so you can use them in any way you want. We need 2 comparators for designing a window comparator, and therefore, if I use half of the LM339, that means 2 of the op amps comparators that I have in LM339, I will be in a position to design a window comparator. So, in the circuit that you see on the screen, you can see you have got 2 op amps from the LM339 IC. This is one comparator, this is another comparator, like you have A1 and A2, and the one of the threshold, the LTP or the UTP, is obtained by using a potential divider. You could have done that even in the previous circuit. That is exactly what we are going to do when we show a demonstration at the end. These LTP and UTP will be normally chosen from the already existing VCC by using a appropriate potential divider circuit. Now, you can see, for simplicity I have taken one of the resistor in the potential divider to be 2R, the other resistance to be R. Therefore, this point, the midpoint between these two, will be 1 by 3R of the applied VCC, and therefore, it will be 1 by 3 times the 12 volts, that means 4 volts. So, this is a HTP or upper tripping point corresponding to 4 volts here. If you look at the other threshold, you see that is also derived from the same 12 volts by using 2 resistors in the potential divider arrangement, and in this case I have 3R and R connected in series to get the potential. So, 3R and R will make it 1 by 4 times the VCC, therefore, this will be 3 volts at this point. So, it is very similar to what we had in the previous circuit. You have 4 volts and 3 volts as the LTP and UTP, as to be precise UTP and the LTP, and I have 2 op amps, and the input is common to the other inputs of both the op amps. Now, in the output there is a slight variation from what you saw in the previous circuit. We do not use any diode here, but we have connect them together, and then this is called a pull up resistor. This 1 kilo ohm resistor which I have connected is called a pull up resistor. So, that pulls it up the output to plus 5 volts level. So, it is deliberately I have kept the output by using a pull up resistor to 5 volts, so that the output voltage can only vary from 0 to 5 volts. It will never go to plus 12 or minus 12. So, thereby the output becomes compatible to TTL logic, the digital logic circuits. TTL logic is one of the good families of the logic circuits, and so where the operating voltage is 0 and 5 volts only, and therefore, if I use a pull up resistor and connect it to 5 volts, the output of the 2 op amps, then the output can never be beyond 5 volts, it will be 0 to 5 volts only. Now, but the actual op amp power supply in this case is a single supply with a plus 12 volts and a ground, as you can see in the circuit. Only the output I use a pull up resistor and connect to 5 volts, so that the output will only go from 0 to 5 volts and not minus 12 volts to plus 12 volts, as in the case of 741 op amp, right. So, this is the circuit, second circuit of a window comparator, where the input is going common to both the op amps, and the two thresholds of the two op amps are maintained plus 4 volts and plus 3 volts by using the potential divider. And now let us see how this circuit works. Now, when the voltage is less than 3 volts, let us take the similar discussion. When the voltage is less than 3 volts, you can see in this op amp, the bottom one, this 3 volts will be more than the input voltage, and therefore, it will be minus at the output, it will tend to go minus at the output, but the output cannot go minus, because the output transistor, which is through the pull up resistor, will become open circuit, it will become off, cut off, and therefore, that nothing will come out, the output terminal is cut off from the op amp. And if you look at the first op amp, this is about less than 3 volts, we already said. So, that means 4 volts is more. So, this will become I considered voltage which are less than 3 volts, right. So, you would find the output will become 0 in this case also. So, in both the cases, both the op amps will be off, and therefore, the output will be 0 volts. The output in this case, actually what is going to happen, this is 4 volts and this input voltage is around 3.5 volts, and therefore, this is less than this, therefore, it will become plus, and this transistor will conduct, the first op amp or the comparator will conduct, and therefore, this pull up resistor will make sure that this voltage is close to 0, the entire 4 volts will be dropped across the 1k and the output will be 0. So, whenever I have a voltage which is less than 3 volts, you find this op amp is off and this op amp is on, and the output will be 0 volts because of the pull up resistor, and you get a 0 volts. Now, when I have input voltage larger than 4 volts, you would find this first op amp, this is larger than this, therefore, it will be minus, and that means the output transistor will be cut off, whereas here this larger than 4 volts means this will be more, and this will be this transistor will conduct at the output stage, and therefore, again it will be 0 volts due to the pull up resistor, this will be 0 volts. So, both for the range of voltages less than 3 volts and more than 4 volts, one of the op amp conduct and try to get plus VCC, and that will make the output transistor to be in saturation, and therefore, the output will show almost the Vsat voltage of the transistor, which is about 0.1, and therefore, it will be very close to 0. Now, for voltages which are between 3 volts and 4 volts, let us say 3.5 volts. If you look at the first op amp, this is 3.5 volts, 4 volts is more. So, this will become plus on this side, but on this side 3.5 volts is more than this also will become plus. Therefore, both the transistors will not conduct, both will be off, and therefore, you will get the same 5 volts at the output. So, whenever the voltage is between 3 volts and 5 volts, the output is 5 volts, because both the op amps will be in cut off and you get 5 volts. Whenever the voltage is less than 3 volts or more than 4 volts, one of the op amp will conduct and make the output transistor into saturation, and therefore, the output will become 0. So, this is what is going to happen, and that is what is shown in the corresponding output graph that you see here. Below the LTP, the output is 0, above the UTP, the output is 0, but between LTP and UTP the output is 1, or output is maximum voltage, in this case plus 5 volts or Vsat, in this case it is plus 5 volts, and so what is that? That is what you get. So in this op amp, compared to the what you saw in the previous comparator, window comparator, you find the output is low all the time, only when the voltage is within the window output is high. In the previous example we had always output high, only within the window the output came low. So this is a variation of the other comparator, and this comparator will be very useful in several applications that you would see later. Now let us go to the demonstration table and take up these two circuits, and I will show you the two different varieties of the op amp comparators, window comparators, how they perform. You see this is the same circuit which we discussed in the first instance. You have two op amps, normal op amp like the 741, you have the two diodes at the output, they are connected together and connected through a load resistor to the ground, and the two inputs you have the LTP and the UTP, here again approximately close to 3 volts and 4 volts, and the other two inputs are connected together. This is the V input. Now what we are going to do is, we are going to put a potential divider by using resistors here to maintain it close to 3 volts and this one close to 4 volts, and the input we are going to give from a millivolt source, and so that I can keep changing the input voltage from 0 to some high value and see what happens at the output. Here below you can see the two op amps. I have used 741, the two op amps are here 741, and I have the two potential dividers here, the two yellow lines actually connect to the two op amps LTP and the UTP, and I have the two diodes here at the output of which I am monitoring using the multimeter what is the output voltage. The input which is common to both the comparator is connected here to a millivolt source, as you can see here, you see here, and this is very familiar millivolt source, we have been using it in all our experiments, and that output is connected as the input voltage. So I am going to change this millivolt source from some low voltage to higher voltages, and what you have to do, you should observe the output of the multimeter. Now the input voltage is very low and the output voltage is around 11.42, which is the saturation voltage, plus saturation voltage. So I have now very low voltage, less than about 1 volt at the input. Now I am going to keep increasing it. As I increase it, all that you have to see is look at the multimeter output, what happens to the multimeter. Now you see at the multimeter all the time, now I am increasing the voltage to 2 volts, now I am going to 3 volts, immediately you see the output voltage has become 0 in the multimeter. So if I now keep increasing, I am increasing the millivolt output from here, and you please observe only the multimeter, you would find when I cross that threshold point, immediately the output has come to again 11 volts. So you see the output is 11 volts for all voltages less than the LTP and more than the UTP, but in between it was having low voltage. Now again I am slowly reducing the voltage so that we can see at the output multimeter it is 0. As I keep increasing, you see the multimeter only, as I keep increasing, suddenly you find the output has become again 11 volts. Now it is about this place that I got 11 volts. Now I would like to measure what is the threshold. This is the upper tripping point. Let us measure what is the threshold by taking the multimeter out from the circuit. I will connect it to the threshold voltage. Let us see how much is that threshold. Yeah, so this is around 3.5 volts. This is a threshold that I have got using the potential divider, and now I measure the input voltage. The input voltage is also 3.52 as you can see in the multimeter. So both the input and the threshold are very close. So this is a place at which the output went to 11 volts once again, and therefore that is corresponding to the threshold. So you can see the comparator is capable of detecting within the two limits, window limits of plus 3 volts and plus 4 volts, and what you get is always the output is 11 volts, and whenever you are within the window the output is low. That is what I wanted to show you. Now let us change the circuit to the next one and let us see the second type of the comparator. Here we see the second comparator, which I already discussed, just now I discussed. Two comparators from LM339 are used, and you have the two inputs where this is the 4 volts, this is 2R and R, that means this is 1/3, therefore it is 4 volts, and here it is 3R and R, and therefore it is 1/4, that means it is 3 volts. So I have a 4 volts threshold here, which is the upper tripping point, and the 3 volts threshold here, which is a lower tripping point, and the other two inputs are connected together, and this is the input I am going to give. At the output we have the pull up resistor 1 kilo ohm going to plus 5 volts, and the output is taken at the bottom. Now I am going to vary this input using a millivolt source, which you have already seen. This is a millivolt source. So I can select, I have put it in voltage, and I can vary from 0 to 10 here, and I can vary in between here, fine adjustment. So I am going to adjust this and try to do that. Now right now, for example, it is at 1 volt, and you can read the voltmeter, it is around 1.21, because if I now decrease it still further, I can get up to 1 volt. Now it is 1 volt, that is what I have set here. I am going to increase the input voltage, and when I cross the lower tripping point, the output you should see using the other multimeter. This is a second multimeter on the output side. This is right now 0.21, that means it is very low, it is low voltage. Now when we know in this comparator what is going to happen is, when my input voltage is between the two threshold, lower tripping point and upper tripping point, the output will be 5 volts here. So that is what you should try to observe. So you should observe what is in the first multimeter on this side, and correspondingly what happens at the other multimeter. So now what I am going to do is I am going to vary the input. Right now the input in this multimeter is 0.99, that is 1 volt. So I am going to increase it, so for example 2 volts. Now it is 1.99, nearly 2 volts. Now I am going to vary this, because this is at nearly 3 volts. I am going to vary it till I reach the threshold voltage, lower till I reach that, still the output voltmeter shows only very low voltage 0.22. Now I am increasing the input voltage, as you can see in the multimeter, in the other multimeter, right, it is increasing. So I keep on increasing. It is 2.4 volts, it is 2.6, 2.8. So you can see now it is about 2.845. Even now the output multimeter reads only 0.22, the output multimeter reads only 0.22. Now I am going to still further increase from 2.85, you see here I am increasing, I have just made 2.87, now you see the output, it has already become 5 volts. So the threshold is about 2.8 volts. Now what I am going to do, I am going to increase still further the voltage. So let me put it in 3, and I will again reduce it to minimum. So the input is 3 volts here, yeah, the input is 3 volts now, and let me see what is output. Output is 5 volts. So now we are within the two window levels, and therefore the output is high. Now as I increase from 3 volts to 4 volts, let us see what happens. I am now varying the input voltage, it is increasing now 3.1, 3.2, etc. At one point you will find the output will go to 0. As I keep on increasing it, I will show you the point where it becomes 0. Yeah, right. Now you see we are at 3.95. If you observe the output, it is still 5 volts. Now keep observing here, I am going to still increase the input, immediately it has come down to low value 0.22 again. So the threshold is around 3.97, close to 4 volts. So, between 3 and 4 volts you find the output is changing from 0 to 5 volts. Below 3 volts and above 4 volts the output is 0. Right now it is 3.97. If I still further increase to 4.9, 5 etc., the output remains at 0.23, that means low. So, the output is low if the voltage is above the upper tripping point. The output is low if the voltage input voltage is below the lower tripping point, but between 3 volts and 4 volts the output becomes 5 volts. That is what I wanted you to observe. Now, I am again bringing it down, and you can see the moment I reduce the voltage the output becomes 5 volts. You can see that it is now 5 volts. So, this shows that the window comparator is low all the time, only within the window region it becomes 5 volts. This is in contrast to what you saw in the first circuit, which I also demonstrated. There it was high all along, only within the window it was low. So, it is just the opposite of this, and this is done using commercially available LM339 comparator, which has got actually this IC which is here, which is a 14 pin IC, it has got 4 comparators inside. So, we have used only 2 of it, that means we have used only half of the IC here, and the other half is also available for other applications. So, what we have seen so far is typically 2 applications of the comparator circuit. They are called the window comparator, where a specific window is generated with a lower tripping point and upper tripping point, especially when the input voltage is within these 2 ranges, the output is in one state, and when it is beyond these 2 upper tripping point and lower tripping point the output is in a different state. And we have seen 2 different examples. In one case beyond the window it was high and within the window it was low, and the second case beyond the window it was low and within the window it was high. So, I have just demonstrated to you by actual experiment also these 2 different type of circuit. The comparator, especially the regenerative comparator that we have seen, is also very useful in another application, which is as an oscillator. So, we are going to now see one more application of the comparator circuit, which is the relaxation oscillator. Now, let me move on to show you the circuit of a relaxation oscillator. You see on the screen you have an operational amplifier, which could be in this case 741 operational amplifier, and you have see the plus terminal is connected to R1 and R2, and immediately I hope you can imagine that this is a regenerative comparator. That means it will have an hysteresis associated with that. The low tripping point and upper tripping point will be on either side of 0. One will be plus some voltage and the other will be minus some voltage. So, with this comparator what we have done is the output point is connected through a resistor R and a capacitor C, and the junction of the resistor capacitor is connected to the inverting input of the operational amplifier. So, it is just a simple circuit with only 3 resistors and 1 capacitor, and what is going to happen, let us assume. Now, if I assume that output initially the output in this case can only be either plus VCC or minus VCC or plus Vsat and minus Vsat. So, if you assume that it is at plus Vsat, then the moment I connect a R and a C to the output, see the output will start charging the capacitor through the R by the time constant related to the RC. You will get the capacitor slowly accumulating a charge due to the output being connected directly to the R and C. So, as the voltage here starts building up due to the charging of the capacitor, this voltage at the inverting input will keep increasing, and the voltage at the non-inverting input is obtained by a potential divider with R1 and R2, and therefore, it will be some fraction of the plus Vsat that we have. So, when this voltage across the capacitor increases beyond the plus fraction of the Vsat that we have here decided by the R1 R2, you would find this input terminal will become higher in voltage compared to the plus, and therefore the output will go to minus Vsat. This is a basic operation of the comparator, we know that. Once it goes to minus Vsat, immediately what is going to happen is this point is no more fraction of plus Vsat, but it is going to be a fraction of minus Vsat, and therefore when I have a minus Vsat connected to the R and C, the capacitor will start discharging through the R towards the output, and therefore the voltage at this capacitor across the capacitor will start decreasing regularly. So when it comes below the fraction of the Vsat that we have at the plus terminal, again you will find the plus terminal voltage will become larger than the minus terminal, so it will again go to plus Vsat. So you find therefore without our switching voltages, the output automatically switches between plus Vsat and minus Vsat depending upon the charging of the capacitor or discharging of the capacitor. Whenever this charging and discharging crosses the LTP and the UTP, you get the output shifting from Vsat to minus Vsat, etc. So I have also shown you the square wave that we get at the output. First is go to plus Vsat and remains there for some time till the RC time constant builds up a voltage which will come beyond the tripping point, and therefore it goes to minus Vsat at the bottom, and it remains again at minus Vsat till the capacitor completely discharges below the other tripping point, then it goes to Vsat, etc. So you find this device is alternate relaxing over the time period RC, and then it is only changing state whenever the tripping points are UTP and LTP. Therefore this is called a relaxation oscillator, and it is a very simple way of making a square wave oscillator. All that you have to have is an op amp with couple of resistors, 3 resistors and 1 capacitor. How do we understand about the frequency of operation? How to get the expression for the frequency of the relaxation oscillator is what we would discuss now. Now before we do that, I have just shown in the graph how the whole thing happens. What you see here is the capacitor voltage. It starts from 0 actually and starts going toward plus Vcc, but it crosses the upper tripping point, the output changes to minus Vsat, and therefore it starts discharging. It starts discharging till it comes to the LTP and again charging, discharging. So the capacitor voltage only moves from LTP to UTP, UTP to LTP, etc., etc. And therefore it is a charging and discharging graph that you get at the capacitor, which can in principle for large time constant can almost be resembling a triangular wave. If you have a large time constant, this will become a triangular wave, and whenever this changeover from charging to discharging happens, the output is actually changing from plus Vsat to minus Vsat, therefore you get a corresponding square wave as shown at the bottom. So the total time period is a period corresponding to one excursion from UTP to LTP and LTP to UTP. So that is what is shown in the figure as period T. So one part of it is half of the period or T by 2 corresponding to this sign. Now we will try and see whether we can obtain an expression for the frequency of operation. So any voltage across the capacitor in general can be written as whatever is the voltage that is already there, we call it initial voltage Vi, plus whatever is the voltage, final voltage that you want to reach, minus the initial voltage. This difference in voltage is responsible for driving a current through the R, charging the capacitor. Therefore the charging voltage is nothing but V final minus V initial. So V final minus V initial is the one which is charging the capacitor, 1 minus e power minus t by 2 RC, where the 2 factor comes because we are looking for t by 2, half the period, how it is happening. So t by 2 RC, this is the equation that we should write. And what is Vc? Vc is the voltage at the capacitor when the tripping happens, and at that time let us say it is beta Vcc. If it is beta Vcc, the initial voltage would have been minus beta Vcc. from minus beta VCC it is building up to beta VCC, then there is a change. So, initial voltage is minus beta VCC and the final voltage it wants to reach, it wants to charge is plus VCC, total VCC. So, the 3 values now we understand. V initial is minus beta VCC, V final is VCC because that is the point towards which the charging happens, and the exact voltage on the capacitor is plus beta VCC just when it is tripping. So, I will substitute these values. Vc is now is plus beta VCC, that is equal to minus beta VCC which is the initial voltage, plus the final voltage is VCC minus beta VCC which is the initial voltage, multiplied by 1 minus exponential t by 2 RC. This is a normal expression for charging of a capacitor, you all know. So, when you simplify this it becomes 2 beta VCC by VCC into 1 plus beta, that is equal to 1 minus e power minus t by 2 RC. Therefore, from this you can get e power minus 2 by RC is equal to 1 minus beta by 1 plus beta, and if you remove the minus sign by inverting it, t by 2 RC will be logarithm of 1 plus beta by 1 minus beta. This is a natural logarithm corresponding to e. So, t by 2 RC is ln 1 plus beta by 1 minus beta, and t is equal to 2 RC ln 1 plus beta by 1 minus beta, where what is this beta? This beta is the feedback ratio which is given by R1 divided by R1 plus R2. This amount of Vsat is being applied at the as a threshold point at the input. Therefore, that is what it shows. So, beta is decided by the R1 and R2 that you choose, and the period is given by 2 RC ln 1 plus beta by 1 minus beta. So, if you substitute all the values correspondingly here, you know R, you know C, you know beta, then you will get the period, and 1 by period gives you the frequency. So, that is how we can get a relaxation oscillator built making use of a operational amplifier in the comparator mode. We have only used in addition an RC to make it as a relaxation oscillator. You get a square wave. You get a square wave with an amplitude plus Vsat and minus Vsat, but we can also vary that output swing by having Zener diodes or several other technique which I already mentioned to you when I talked about the comparator. So, for example, you can use 2 Zener diodes back to back connected at the output, then depending upon Vz, let us say plus 5 volts is the breakdown voltage of the Zener. So, you will get plus 5 to minus 5 excursion instead of plus Vsat to minus Vsat, which in usual case will be plus 12 to minus 12 or plus 15 to minus 12. So, you can modify the output swing to any value you want, either plus 5 to minus 5 or 0 to plus 5 and things like that, and thereby you can have a simple square wave built around a comparator. Having said that, I would like to now show an actual circuit working and explain to you about the circuit. So, here you have the relaxation oscillator, you can see the operational amplifier which is again here 741, and the plus is connected to a potential divider, and here the potential divider is both having 10k plus 10k. So, it will be half of the Vsat that you will get here as a threshold. When it is plus Vsat, it will be, for example, plus 12 volts is applied voltage. So, 6 volts will be the threshold here. When it is minus, it will be minus 6 volts, half of that. And then to the negative input we are giving from the output a resistor and a capacitor in series, and the junction is given to the non-inverting input. So, this is the simple relaxation oscillator. The same circuit is wired here, you can see the op amp, and this is the 2 resistors that you have here, both are 10k from the color code you can observe, and the midpoint is connected to pin number 3 which is the non-inverting input. Pin number 2 is connected to the RC here, the R is 100k and the capacitor is about 0.1 microfarad. So, I have the same circuit wired here, and what we have done is I am monitoring the voltage obtained at the capacitor end as well as at the output. So, I measure the output voltage waveform here as well as here, both the points. Now, let us see what happens. When you look at the oscilloscope, I would like you to see the oscilloscope. Now the bottom trace is corresponding to the voltage across the capacitor. You can see it is charging and then discharging, and this should be corresponding to the LTP, and this should be corresponding to the UTP. So it keeps on moving between the two limits UTP and LTP, and whenever that transition happens at that stage, it goes from low to high, minus Vsat to plus Vsat and again to minus Vsat, etc. That is what is seen here. If I increase the amplitude, you will be able to see much better the charging curve. This charging curve will become more straight if I use larger resistor or larger time constant, the product RC. It will become much more like a triangular wave. Right now it is not resembling a triangular wave because it is basically charging and discharging that is happening, and you get a square wave here. You have nearly about 2 divisions, and that corresponds to nearly some 12 volts or so if you look at the dial of the oscilloscope. So you can get a square wave, and you can also get a triangular wave if you properly choose your RC time constant, RC values. You can also get a triangular wave. Once you get a triangular wave and a square wave, you can get several other associated waveforms whenever you want. So it is a very simple scheme by which you can get a square or a triangular wave by using an operational amplifier in the form of a comparator. That is the application of the comparator for preparing a free running square wave oscillator. So the output, again I said, can be limited to plus 5 volts or minus 5 volts or 0 to plus 5 volts by correspondingly connecting here to Zener diode or a Zener diode and the series resistor as the case may be, and you can limit the amplitude to any desired value that you would like to have for a given application. So far we have seen different applications of the comparator, where the comparator can be used as a window comparator to identify a set of voltage values which are within a maximum and minimum limit. We have seen 2 different types of circuits which can be used as window comparator, and we also saw a very useful application of the comparator in the form of a relaxation oscillator, where we have just used a couple of resistors and capacitors to have a square wave output at the thing. Now we can also, for example, have the R value, RC combination. You have the R or the C. You can vary the R or the C as the case may be, and thereby you can have a variable frequency or variable period square wave or triangular wave oscillator. Simply you remove the 100K resistor that you saw in the circuit and replace it with a 100K potentiometer, variable resistance. Then as you vary the resistance, you would find the time constant is changing, therefore the upper tripping point or lower tripping point will be reached sooner or later as the case may be, and correspondingly that will correspond to a change in the period, and that means the frequency of the output will be changed by changing the R value of the RC combination. Again, if you change the capacitor, you will get much larger ranges of frequency variation that is possible. In most of the commercial function generators that you come across in a laboratory, both the C and R are also varied in a similar fashion. If not in this circuit, the basic principle of varying the frequency is you vary the resistance continuously for a range and then switch the capacitor to a new value by 1 order or so, and again vary the resistance for getting the intermediate frequency values. So by a combination of variable resistor and switched capacitors, you can achieve very large frequency range for these circuits. So in principle you can prepare a very simple square wave oscillator by making use of an operational amplifier in the nonlinear comparator mode. Apart from that, operational amplifier nonlinear applications have got many more similar applications. So what perhaps we would like to discuss next will be how we can measure very small AC voltages. If I have an AC voltage normally, if for example if the AC voltage is only 0.5 volts, if I want to measure it without amplifying it, there is no way I can do it, because if I now try to rectify it using a normal silicon diode, you know, normal silicon diode requires a minimum of 0.6 volts or 0.7 volts for it to conduct freely, and therefore if I apply 0.5 volts AC sine wave, it will not be able to forward bias the diode, and therefore after rectification I will not get any voltage at all. So you find a normal diode cannot be used for voltages which are very low in magnitude like 0.5, 0.4 and things like that. But you would see maybe in the next lecture that by using an operational amplifier along with a diode, I will be in a position to make the diode much more ideal diode without having to have about 0.6, 0.7 volts across it. Even when it is very small in the order of microvolts, the diode will start conducting and it will be able to behave like a rectifying diode, ideal rectifying diode, and thereby we will be able to study very low level signals also without any problem. So the applications of that active diode circuits, the principle of operation, how it can be used for full wave rectification, half wave rectification, how you can make a peak detector with the active diode, and you can also make clipper and clamping circuits, which we have already seen when we discussed about the applications of diodes initially, can all be discussed making use of this active diode. So we would perhaps spend the rest of the lecture next time on the active diode circuits and applications. Thank you.